In this video, we discuss the extremes of the function, both through infinite limits or limits as the input is approaching large numbers, infinity. So the concept of infinity is kind of like zero, actually a bit complex. In simple terms, when we say that x approaches infinity or x increases without bound, we mean that the value increases constantly, but it goes past anything you can think of. So it's not a real number, it's a concept. We'll often also say that x increases without bound or x goes to infinity in its place. Now this next example would work a little better if we were in person, but let's try it anyway. The truck driver problem. The basic premise goes like this. Suppose you have a truck driver that travels from a warehouse to a city and back again. On the trip down, he goes X miles per hour. On the trip back, he goes Y miles per hour. But overall, for the whole trip, he averages 50 miles per hour. So if I tell you how fast he went on average to go to the city, can you tell me how fast he went to come back from the city so that overall he averages 50 miles per hour? Now, the first guess I usually say is, hey, what if he went to the city at a rate of 50 miles per hour? What speed should he come back at? So overall, he averages 50 miles per hour. Eventually, someone is brave and will say 50 miles per hour. And that's right. That's actually the correct answer. But if he travels from the warehouse to the city and travels 40 miles per hour, if he wants to come back overall so that the overall speed is 50 miles per hour, his speed back is not 60. It has to be more. I'm going to show you why. And that will introduce one of our new limits. So here is a visual model of what's going on. We have the warehouse in the city, and the distance between them is unknown. It's not mentioned in the problem because it actually doesn't matter. So we'll call that distance d. X with the speed from the warehouse to the city, and t is the time you take. And the return trip is done at a speed of y, whose time overall is s. So we know that the overall time it takes to the whole trip would have to equal the time going from the warehouse to the city, t, plus the time it takes to go from the city to the warehouse, s. But we know exactly the time it takes overall because the distance going from the warehouse to the city and back again is 2d. But we know the average speed is 50 miles per hour. So we just divide the two. That's the total time. Notice the total time is fixed. Next, the amount of time to go from the warehouse to the city would be the distance you travel divided by the speed you travel at, and the time it takes to come back from the city would be the distance you travel divided by the speed you travel at. That's an equation that relates the variables. Notice though that d is not zero, because if d is zero, this is a silly problem. Then the warehouse and the city are in the same spot. There's no traveling to do. So d is not zero. We can then cancel all those d's, and we can then solve for y. When you do so, you get that equation. Now notice what happens if I were to evaluate this at different speeds going from the warehouse to the city. So for example, if I were to plug in 50 for x, I should get 50 for y. If I plug in 40 for x, I said we wouldn't get 60 for y. And here is a whole bunch of different evaluations. I've picked different speeds as those speeds approach 25 from the right. So they get closer and closer. Notice that as the speed going from the warehouse to the city is getting closer and closer to 25 from the right, the speed coming back, though, is getting incredibly large. Now that usually surprises people. In fact, this model predicts that if you go just a little bit over 25 miles per hour, you have to come back faster than the speed of light, so that overall you just average 50 miles per hour. This is counterintuitive for most people, but it's not hard to understand. Just think of it in terms of the resource we actually have. The only resource we have is time. The amount of time overall for the problem is fixed. Well, if you spend most of that time just going from the warehouse to the city, you have very little, a microseconds amount of time to come back. But the amount of distance you travel come back is still fixed. So if the distance is fixed, but the amount of time is really close to zero, well then the speed must be astronomical. So let's talk about infinite limits informally. Consider you have an apple. Now you want to share it among a number of people, But each of these people demand to have at least 1/8 of the apple. So how many people can you feed? Well, of course, that would just be 1 divided by 1/8, which would be 8 people. You can feed at most 8 of them. But the people you're working with are really good at sharing. So now they're willing to take at least only, like, I say, 1/100th of an apple. Now how many people can you feed? Well, in that case, it's still the same division. It's 1 divided by 1/100th, which is now at most 100 people, which is more. This is essentially the idea behind limits, at least the infinite ones. If you go and take a constant and divide it by a value that's really close to 0, the overall division becomes very, very large. So here is a basic definition for infinite limits. Let f of x be a function defined for all x in an open interval that contains c, except possibly c itself, because we don't care in that case. We say the limit of the function as x approaches c is infinity, or that f of x increases without a bound as x approaches c. And we'll write this notation. Provided that the values of f of x are arbitrarily large just by restricting x to be sufficiently close to c. Now there's similar definitions when you take limits to the right of c and left of c, but you should notice though that the limit here does not exist because it's still approaching nothing. It's just getting incredibly large. So the function must by default be discontinuous if the limit is infinite. So let's use our numerical and graphical methods in order to guess what this limit would be. Now if you look at a table of values, letting x approach 3 but bigger than 3, and look at the corresponding function values, notice that the function values are getting incredibly large as x gets fairly close to 3. At the same time, if you look at the graph of the function and look at the line x equals 3, when you do so, take an x value that is more than 3 and look at the corresponding point on the graph. Now when you do that and let the x value approach 3 from the right, notice that the point on the graph travels to the left but rides the graph going upwards and just keeps going up without a bound. So then we're led to believe, based upon this evidence, that this limit should be infinity. So looking at these graphs, I'd like to know then, what are the limits from the left and the right? Now looking at the first one, if you imagine the line, which is at x equals 1, and you come from the left, see how the function's graph just goes down without a bound? That limit then would be negative infinity. If you come from the right, it goes up, so that'd be positive infinity. And in each of these cases, you're not saying the limit exists. It doesn't exist, because it doesn't approach a value. But you're describing how it doesn't exist. We'll just keep with the normal law that you saw before. Since the limit at the left and the right don't have the same behavior, the only thing you could say with the limit as x approaches 1 is that it just plain does not exist. In the other case here, all these limits then should be negative infinity, because the function is decreasing without bound from the left and the right, and overall it's decreasing without bound, irregardless of what side you come from. So we need some general way to find the limits of these functions to say that they're infinite or they're going to negative infinity using some kind of analytical method. So the general idea goes like this. If you have two functions, f and g, and they're both continuous functions on an interval that you're interested in, and the limit of the numerator is going to a non-zero number, let's say positive, the limit of the denominator is going to 0. At the same time, though, the function in the denominator is always positive. That would then say that the limit of the ratio of those two functions would go to positive infinity. Now, in layman's terms, it's saying if the limit of the top is non-zero and the limit of the bottom is 0, and the division is always the same sign for the choice of values you're using, then the limit is either positive infinity or negative infinity, depending upon the sign of that division. So then you can use this also for the limits from the left and the right. I just gave you a larger version of it. So for example, if you wanted to say, let's say, and do this limit here, notice that the limit as x approaches 2 from the right, if you look at the numerator, that limit is 1. It's positive. And it's near 1, so it's always positive. The limit of the denominator, though, that limit's 0. But since x is approaching 2 from the right, that means it's approaching 0 from the right, so it's always positive. So the top is positive, the bottom is going to 0, but is always positive. This limit then would have to be infinite. Trying another one, same idea. If I wanted to know how to find this limit, I would go ahead and take the limit of the numerator and the denominator. The limit of the numerator, as x approaches 1 from the left, would then be 2, which is positive, and it'd be near 2, so it'd always be positive. And the limit of the denominator, being the natural log of x, as x approaches 1, that's approaching 0. But if x is less than 1, the natural log of that value is actually a negative number. So the numerator is always positive and near 2. The denominator is always negative but near 0. So the limit is infinite, but this time, because of the division, it would then be negative infinity instead. So that's that one. Try it again. If I wanted to find this limit as x approaches 0, notice not left or right. So if x just approaches 0, the numerator approaches negative 3. So it's always negative. It's always near a negative number. And then the denominator, though, if you let x approach 0, the denominator goes to 0. Notice the numerator is always negative because it's near negative 3. The denominator, though, is always being squared, so it's always positive. So we have a negative number divided by a positive number. The result's got to be a negative number, but we know since the top is not 0 and the bottom is 0, the limit here would then be negative infinity. One more time. So if you look at this particular function, the cosine divided by sine, which you guys know is cotangent. If you let x approach 0 from the right, the cosine as x approaches 0 is 1, so it's near a positive number, so the top is positive. The denominator, though, the sine of that x as x approaches 0, that would be 0. But since x is approaching 0 from the right, it's more than 0, so the angle is in the first quadrant. So sine and cosine would be positive that entire time. So the division is positive. So the top goes to 1, the bottom goes to 0. The ratio is always positive, so we have to get positive infinity as the answer to that problem. Now, if you consider the other remaining 4 trig functions, they're all ratios of 2 continuous functions. So then those functions are essentially unbounded behavior, either positive or negative infinity, where they're not defined. You have to figure out which one by considering sign arguments. So for example, the limit of the tangent of x as x approaches pi over 2 from the left, that's got to be infinity. Because if it's less than pi over 2, you're in quadrant 1, tangent's positive, and the function's got to be unbounded there. So it's got to be one of the two. The limit of the secant of x as x approaches pi over 2 from the right would be negative infinity, because the secant is not defined at pi over 2, so it's got to be unbounded behavior there. And because it's really 1 over 0 when you evaluate it. And if x is approaching pi over 2 from the right, then the angle is actually in quadrant 2, and the cosine, and therefore the secant, is negative. So the answer must be negative infinity. You get a similar result for logarithms. All the logarithms are not defined for any values 0 and below, but as you approach 0 from the right, the natural logarithm and all the logarithms actually decrease without bound. So for example, the limit of the natural log of x minus 5 as x approaches 5 from the right, if x approaches 5 from the right, then x minus 5 approaches 0 from the right, and the natural log of that then is unbounded and decreases without bound. It goes to negative infinity. On the other hand, though, if you take the limit of the natural log of x minus 4 as x approaches 4 from the left, then it's true as x approaches 4 from the left, x minus 4 approaches 0. But it approaches it from the left. It's actually always negative. And the natural log doesn't exist for those values. So since there's no function values, you can't say anything about the limit. There are no values to worry about. So in that case, you can only say it does not exist. Now, again, remember, all these limits don't exist because you are not approaching values, a single number. But we're just describing, where possible, how it doesn't exist, if we can say that it increases or decreases without a bound. Now that we have a better handle on infinite limits, let's attach some kind of graphical concept to it. So, if one of the 4 limits from the right or the left is either positive or negative infinity, then we will say that the graph of the function has a vertical asymptote at that x value. So the line x equals a in this case would be a vertical asymptote. Now, just to show you an example, let's suppose that the limit of some function as x approached, let's say 1, let's say that was negative infinity when we come from the right. Then the graph, if here is the line x equals 1, the graph would then have to decrease without bound as you come from the right. Don't be fooled though. All we need is one of these four things to be true. So I could have, in addition, that the limit of the function as x approaches 1 from the left, that might be 0. So the graph could look like this to the side and have an open hole there. Also, having a vertical asymptote does not mean the graph can't be defined at that line. It can be. For example, here I could say f of 1 is going to be 1. I would then have this filled in dot right here on the graph, and that's perfectly fine. This function still has a vertical asymptote. And notice that the graph crosses it. So saying the phrase an asymptote is a line that the graph gets close to but doesn't cross is not true. So please don't say it. So let's consider, how do you find out where a function's graph would have vertical asymptotes? Well, you can only have a vertical asymptote if the limit from the left to the right of a single number is infinite. But that can only happen if the function is discontinuous. So we just find potential candidates for discontinuities, and then we try to figure out, well, what kind of discontinuity it is. So in this particular function, I would go and find where is the denominator 0, because those are the only discontinuities for that function. So I'll just solve that x times 1 minus x would then equal 0, and I'll solve that for x. Clearly the solutions are x is 0 and x is 1. So we have that the function is discontinuous at these values. But that does not mean we get a vertical asymptote there. We have to check the definition. So normally you would check the definition by going to take the limit of the function as x approaches these values from the right separately and the left separately. But here, actually, to save time, I'm going to go take the limit as x approaches 0. That will then just be the limit as x approaches 0 of negative 4x squared all over x times 1 minus x. And that is the same as the limit as x approaches 0 of negative 4x all over 1 minus x, because the x is not 0. So there's a common factor of x, which is non-zero. We can cancel them. Then this is then a rational function, and 0 is in its domain. We know it's continuous there. So we can just plug in the number to get the answer. That would then be 0. Notice it's not infinite. And this means then the limit to the right is also 0. The limit to the left is also 0. This function does not have a vertical asymptote, actually, at x equals 0. On the other hand, if you were to take the limit of this function as x approaches 1 from, let's say, the left, then the numerator is approaching negative 4. So it's always negative, at least for numbers really near 1 for x. The denominator would be a 0, because you plug in 0, you plug in 1, you get 0. But if x is near 1, the x factor is near 1, but the 1 minus x, that would be getting near 0, but x is less than 1, so 1 minus x is always positive. So the numerator is always negative, the denominator is always positive, the numerator is going to a non-zero, the denominator is going to 0, so in the limit, by the rule I've given you, this has got to be negative infinity. That's enough to say then that x equals 1 is a vertical asymptote for the graph of y equals g of x. And unfortunately, these are the steps you have to go through in order to find out or to verify that a function has a vertical asymptote. You now have to check limits. Now that we have a handle on infinite limits, let's consider the other extreme. That is, a function's values as the input were to either increase or to decrease without bound. So as an example, consider a population of deer. Now that deer population, its growth, might be limited by the amount of food, the amount of space, or of course other resources. So pretend that this function, P of t, gives you the population of deer in a certain forest in terms of the number of years that have passed. I'd like to know if this really is the population based upon the resources available to these deer. Is there an upper bound to it? That is, can the forest only sustain so many deer? Well, to investigate that, let's just try the numerical technique first. Let's just evaluate the function at different time values. So I did that for about every 5 years, and after all that, I started skipping by tens. Notice, though, that if you consider that time increases without bound, it appears that the population is growing, but the rate at which it grows decrease. That is, that it gets less and less gains for the same amount of change in time. In fact, it appears that the population is getting really close to the number that's in that numerator, 2,000. Now, that's not a course of proof. This is just numerical data. I'm just looking at a few evaluations and from there gleaning what I think happens in general for all time values as the time just increases without bound. It's not a very good argument. So let's move up and try the graphical argument. So here is the graph of the function. If you go and look at a certain time value and look at the population, it will correspond to a point on the graph. But if you allow time to increase, the population then will also change, and the graph, the point at least on that graph, will move on this graph going towards your right. As it does, notice how it never gets above a certain line, and that line, the horizontal line, would be y equals 2,000. And in fact, that appears to be the limiting value of the function. The function seems to never ever get above that line because the point on the graph never gets above that line. So from this evidence, I would think that in the limit, the population is never above 2,000. And in fact, the limit is 2,000. I'll have to show you that later. This time, in the interest of time, I'll just give you all the definitions right up front. So suppose that you have a function that's defined for all x bigger than c. We then say the limit of the function as x approaches infinity is a value L, and write the notation as you see. Provide the values of f of x can be arbitrarily close to L when just restricting x to be sufficiently large. Now there's a similar definition as x goes to negative infinity. The only difference is that we're decreasing the x without bound instead of increasing it. So a horizontal asymptote is just a line y equals L so that one of two limits is true. Either the limit of the function as x were to increase without bound goes to L, or the limit of the function as x decreases without bound is L. Now you have to be careful. The way you should interpret the result is that it's as if there's a big funnel, and if the function approaches L as x increases without bound, that means then that the function values just get closer and closer to the line. It says nothing about crossing it. So it's like it gets into a funnel and the funnel squeezes the graph to become more and more like the line. Notice that you could have a horizontal asymptote to one side or the other, but you don't have to have both. And if you do have both, they don't have to be the same thing. They can be different lines. Also, if you have a horizontal asymptote, the definition doesn't say anything about not crossing it. After all, look at my picture. I drew it so that it crossed the line a bunch of times. And in fact, there are functions that have horizontal asymptotes that cross that horizontal asymptote an infinite number of times. So please do not say a asymptote is a line that the graph gets close to but does not cross. The does not cross part is just not true. Let's get an informal understanding of limits at infinity. Consider that apple once again. You want to share it equally among 20 people. So then what portion of the apple does everybody get? Well, there's one apple. There's 20 people. So everybody gets 1/20th of the apple. Notice that's not very large. That's close to 0. Well, but these are sharing people. If you want to go and share that same apple again among, let's say, 1,000 people, each person now only gets 1,000th of the apple. That's really close to 0. Well, this gives you the basic idea behind limits of infinity. The basic idea that we use is that if you ever take a non-zero number but divide it by a large number, the result is really super duper close to 0. A really useful limit that we'll use to help us compute other limits is that if you give me any constant and any positive power, if you have the constant divide by x to that power, and x is either going to positive or negative infinity, then that limit's 0. The reason is because if x is very, very large, then x to a power, positive power, is also incredibly large. You would then be dividing a very large number into a constant, which would then be really close to 0, as you just saw with the apple. The only condition is that the expression must exist. So if you had, say, x to the 1/2 power, that's the square root of x. If you let x go to negative infinity, well, then x would be negative eventually, and the square root of x doesn't exist then. So just as an example, if you had to do this limit, it's a constant over a power of x where x is going to infinity, and the expression always exists for those x values, so that limit's 0. If you had to find this limit, again, you have a constant over a power of x, that's a positive power, and x is going to infinity, either negative or positive. So since that expression exists, the limit's 0. While this one, you have a constant divide by a power of x, but here, if x is going to negative infinity, the square root of x doesn't exist for those values. That limit just doesn't exist because there are no values approaching anything. So let's go and compute a few of these limits. So the limit of x plus 2 over x minus 3 as x goes to infinity, we don't know how to compute that yet. But if you go and take that expression, and since x is not 0 because it's becoming incredibly large, I can divide in the numerator and the denominator x. By doing so, we get that expression. But then by the limit laws, you would then get the limit of 1 as x goes to infinity plus the limit of 2x as x goes to infinity all over the limit of 1 as x goes to infinity minus the limit of 3 over x as x goes to infinity. So you can see the whole reason to divide by x was to have certain limits appear. We essentially complicated the expression specifically to enable us to find the limit. That then is equal to 1 plus this limit 0 over, you have 1 minus, and the limit of 3 over x as x goes to infinity, that's also 0. So the limit is 1. That means then that y equals 1 is a horizontal asymptote for the graph of the function y equals x plus 2 over x minus 3. Now, in order to do that limit, you notice I chose to divide by x. The reason I did that is I want to make sure that in the denominator that I don't get 0 when I do all the limits. So one way to guarantee doing that is to always divide by the largest power of x, or some combination of that if you have multiple functions. That way, in the end, you'll always have at least 1 in the denominator. So here, I will then take the limit as x goes to negative infinity. I'll divide everything by x squared to get 4 over x plus 2 over x squared. I'd have a 1 minus 5 over x minus 3 over x squared. And since you saw me do it already, to take this limit, the limit of a quotient is a quotient of limits, a limit of a sum is a sum of limits, and a limit of a difference is a difference of limits. So then taking all those separate limits, you would get a 0 plus a 0. You get 1 minus 0 minus 0. The answer, therefore, is 0. So that function has a horizontal asymptote, y equals 0. Now, something you should be aware of is that in these limits, I'm only going in one direction. So it's possible if I go the other way, so if I went to negative infinity instead, you might get a different horizontal asymptote. But actually, if you look at all the work, it never matters that x is negative eventually. In the end, I still get the same answer. The same with the other function. If I made this be positive infinity, I would change that to be positive infinity, but the result is still the same. So these functions are rational functions. If a rational function has a horizontal asymptote, that means that one of the limits as x goes to infinity or negative infinity would have to be a number. But if you just change the infinity to its other type, you'd get the same limit. So for rational functions, if you have a horizontal asymptote, it's the same asymptote in both directions on the graph, either positive or negative infinity. That is not true for other functions. Many times for other functions, in one direction you'll have an asymptote, and the other you will not have a horizontal asymptote, or you'll have something completely different. In fact, let's do an example where the limits are different. This particular function has two horizontal asymptotes, but they're different lines. To see why, notice that for this first limit, you can write this as the limit as x goes to infinity of, you get 2x plus 2, but since x is going to infinity, x eventually is positive, so the absolute value of x is equivalent to x. So I'll just replace it with what it's equivalent to. You can then divide each of these by x to get 2 plus 2 over x all over 1 minus 3 over x. And then by using the limit laws, that would then be 2 plus 0 over 1 minus 0, and that is 2. So the graph has a horizontal asymptote of y equals 2 going to the right as x goes to infinity. On the other hand, though, if you take this limit as x goes to negative infinity, once again, x is eventually, in this case, negative. So the absolute value of x then is not equivalent to x. It's equivalent to negative x. Because if x is negative, the opposite of it is positive, guaranteeing you get the absolute value of the answer. Then you have minus 3. Here then you can then divide each term in numerator and denominator by x to get 2 plus 2 over x divided by negative 1 minus 3 over x. And I think you can see then the limit now is negative 2. So this function would have two horizontal asymptotes. As x increases without bound, the graph goes towards the line y equals 2. As x decreases without bound, the graph approaches the line y equals negative 2. Last two attempts. I'd like to know these limits. These involve some more trickery. Notice that this time, this would then be the limit as x goes to infinity. I'm going to rewrite that as the sine of 1 over x divided by 1 over x. Why? Because as x goes to infinity, 1 over x goes to 0. But that means that this limit is 1, because we've seen that before, right? The limit of an expression when it goes to 0 of the sine of that expression over that expression, that would then be 1. We've seen that before. So that's it for that one. That's pretty easy. You might not like the result. So sometimes people use a in-between step. If you don't like this, instead, you could say let theta equal to 1 over x. Then, x going to infinity implies that theta is going to 0. So the limit then would become the limit of the sine of theta over theta, and we just have to insist that theta is going to 0. But we have to be careful. See, just because x is going to infinity does not mean theta is going to 0. Being a little more careful, notice that if x is going to infinity, then 1 over that value, 1 over a positive value, is always positive. So theta isn't approaching 0 because theta can't ever be negative. It's actually approaching 0 from the right. But still, if I'm taking this limit, as theta approaches 0 from the right, the limit is still 1. Let's try another one, last one. To find this limit, notice in the denominator, the highest power of x appears to be x squared. But it actually isn't because of the square root. You have to take that into account. So you're going to divide by the square root of x squared. Now remember though, the square root of x squared is really the absolute value of x. So for these x values, as x is going to negative infinity, the absolute value of x is equivalent to negative x. So sometimes I'm going to divide by the square root of x. Sometimes I'm going to divide by what's equivalent to negative x. So this will then be the limit as x goes to negative infinity. In the numerator, I'll divide each of those by negative x. You get negative 1 minus 2 over x. But in the denominator, I'll take this entire square root and I'll divide it by the square root of x squared. I do that because since they both have square roots, you can use a single square root and just divide the radicands. That gives you when -1 minus 3 over x, you get a single square root. And now I just take everything in the square roots, x squared plus 3x minus 5, and I divide each of those by x squared. That would then give you 1 minus 3 over x, well, plus 3 over x, minus 5 over x squared. Now it's easy to find the limit by using our limit laws. The numerator would be -1 minus 0 all over a square root of 1 plus 0 minus 0. So the answer is -1. This function has a horizontal asymptote as x goes and decreases without bound, and that would be y equals -1. So now that you've been introduced to the infinity symbol, please remember it's not a number, it's a concept. It means it's something that's growing without a bound. Whatever you think it gets to, it just went past it. So in a limit, if you ever have infinity with other symbols, you need to know how to handle that. So then I've given you the formal way to write it and then the informal. The informal is a lot easier to understand. So if you take two functions and were to divide them, if the numerator is approaching a constant, but the denominator is increasing without bound, then that should approach 0. So in formal language, a constant divided by infinity, that's 0. So another one, the one at the very, very bottom, if you have two functions that are both increasing without bound, then the limit of that also increases without bound. So informally, infinity plus infinity is not to infinity, it's infinity. Infinity means a large number, so if you take infinity, large number, plus infinity, large number, you get infinity, large number. So to give you an example of what I mean, let's do this limit. So the limit of a sum is the sum of limits, but the first one, that limit is 5, while the second one, 1 over 0, as 0 is going to right, that would then be going to infinity. So this, I'm thinking, has the form of 5 plus infinity. Well, infinity means really large number getting constantly larger. So it's like a billion, 2 billion, 3 billion, and it's getting larger. If you add 5 of that, it doesn't do anything. It's still large and it's still getting larger. So the answer here would then be infinity. And notice there's not really much work you can do. You just write down the answer. And that gives you a good understanding of infinity and how it relates to limits, either the infinite limit or limits at infinity. We're now ready to go and continue back with our original path, talking about rates of change and tangent lines.